Okay, this is math 408. We're packing in L functions. And so before we do the hexagonal tiling is the best, in class beforehand, I had passed out the handout that we're going to discuss, and there was a remark about how amazing it is, in either in a positive or negative way, that it's getting 90%. That, oh my God, it only gets 90, or oh my God, it gets up to 90, depending on which way you want to look at things. And then we were talking about, well, could you do something better than a hexagon, which hugs things very closely? It was remarkable, use an octagon. But the problem with an octagon is the octagon doesn't tile. And so I thought I would just briefly show one of the many games I play when I go into elementary schools, or at least when I used to go into elementary schools. I have done this by Zoom. So this is the I Love Rectangles game. So I love rectangles. I'm like the Farmer Brown from the calculus class with my pen for my students, I'm sorry, for my cows. Has to be a rectangle. I will not consider any other shape. And if you want to maximize the area for a given perimeter, what do you do? Yes, you make it a square. And in fact, there's a nice generalization where if instead of having having to do all four sides, you only have to do three sides, and you have to do a rectangle now where you get one side for free. What's the optimal shape now?
Half square.
Half a square. Do you know the one-line proof that it's half a square?
Reflected about that line.
Reflected about itself. So basically you have Aquaman down here, and oh, Batman has to be capitalized. Batman up here. And each one of them is independently trying to find what maximizes. And so it's the same as trying to maximize with twice your perimeter. And so that has to be a square. So you get it for free. It's a really nice symmetry. Okay, so switching back, it was asked, well, what if we didn't have all circles of the same size? And that's exactly what I want you to be doing in a class like this, is I want you to be taking things that we're doing and asking, how can we push this to something new to look at? The most important thing is to generate questions. After a while, you all learn the same techniques. And if I give certain questions, it's clear what's going to come from it. And so in the I Love Rectangle game, you start off with a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4, 5 by 5, and so on and so on and so on. You have exactly one copy of each rectangle. If you can place two of these squares down, you can't put one on top of the other. They have to be on the plane touching, such that their shape is a rectangle. You win. You know, I can place one. Can you place two? So you only have one of each square. Is there any way to place two of these squares down? No, why not? Can't stack on top, and they have different sides. So the I Love Rectangle game, if this is all it is quite boring. So I have to give you additional pieces. I can't just give you one of each. What is the least amount of extra stuff I can give you in terms of squares? I'm cheap. What's the minimum amount of additional material I can give you? I give you a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4. I have to give you something else. I have to give you something twice. Which piece should I give you twice? The 1 by 1. So now I'll give you two 1 by 1s. Can you put two of these down and form a rectangle? Yeah, the two 1 by 1s. What do we put down now? 2 by 2. And there's a reason why I'm putting them down in this order. What do I put down now? 3 by 3. And now what? 5 by 5. And so you're going to get the Fibonacci spiral. And so you actually can tile the plane using the Fibonacci's. And my daughter, with a little bit of help of my son and I, made this out of fuse beads. We actually expanded later to get to 55 by 55. It takes a long time to get them that big. All right. that was just inspired by the start of class. Okay. Now, let's see how well this works. Okay. I'm going to share the screen now. So if you are in class, you should have a printout of the paper. If you are at home, I've sent you an email with the paper, and I will also be projecting it. And again, I'm experimenting this semester with how to teach a senior seminar. It's been a while since I've done it. We have a small class. We actually have the ability to have class discussions and participation, which is nice. And I want to try to train you for situations that are going to happen in real life. What will happen in real life is you'll be at a conference and someone will be giving a talk. Hopefully a good talk. Hopefully a clear talk. And you might want to ask them questions afterwards. If you can, if you are giving a talk later in the conference and your talk is related to work of theirs, try to reference something they said. No one is ever upset when people refer to their results. When I was at Brown, the undergraduates had a wonderful conference each year, and John Conway was the speaker one year, and he was very wonderful. He actually adjusted his talk based on student presentations earlier in the day. And to have a plenary speaker do that was just truly wonderful. So I searched on the web for a simple proof of Thue's theorem. Not surprisingly, I found a paper titled A Simple Proof of Thue's Theorem on Circle Fractions. Let's look at it. It's only 4 pages. So you could easily convert this to a couple of slides. And so rather than converting it to slides, I want to just go through, and I want to go with you as to how would you look at a paper like this? Do you trust it? So is there anything that makes you think that it might be trustworthy? Yes?
You have to go and look at the author.
So you can look at the authors and you can look up and see what have they done. What else might make you think that maybe I could trust it? Yes? It's in LaTeX. And so there is a professor who used to teach here who still did things in Microsoft Word. For the most part, if it's in Microsoft Word, that is a warning symbol. A warning sign.
Presumably it was published somewhere.
Ah, now that's interesting. So right now, this is an archive copy that I have. So you could look up and see, was it actually published somewhere?
Hopefully they don't pick up paid.
Yes. But there are a lot of journals that just publish anything. Yes.
They have their credentials listed.
Yes, so you can look and see where are they. And do these look like legitimate institutions? It's not what's the matter you. Cultural extra credit if anybody knows what what's the matter you is from. The Rocky and Bullwinkle Show. So if any of you are Simpson fans, any Simpson fans there? What's the middle initial for Homer and Bart? They both have the same middle initial. It's J after the middle initials of J from the Rocky and Bullwinkle Show. The creator of The Simpsons, Matt Groening, was paying homage to that show. So let's start looking at it. So when you're reading a paper, what you can do very quickly is see what matters and what doesn't matter. So I referee a lot of papers just from general journals. I'm also one of the managing editors of the Journal of Number Theory, so I have a lot of papers coming in. If anybody wants to referee a paper and have this on your CV or just have this experience before you apply to graduate school, happy to share that with you. When you're trying to decide whether or not something is correct or not, you can just look at something and say, text that doesn't really matter. So basically, all the stuff over here is basically just saying what we're going to prove. There's really no content in there at all. The result is that the density of the circle configuration is pi divided by square root of 2, or about 0.91%, a little bit under 91%. And so it then lists, some people and where the proofs are. Doesn't actually have references. So you can't just quickly look up those places, which would be very useful. And it says that there were some issues with Thue's original proof, and it was thought to be maybe incomplete. The first complete and flawless proof is credited to Thue. And then later different proofs were proposed by different people. I would have had references to those works. Make it very easy. All right, so now we start to have some text coming in here. So a circle configuration is saturated if it is not the proper subset of another circle configuration. So what do you think this means at a high level? We have some circle covering of the plane. Yes.
Means if we could just add another circle in it, then the current one wouldn't be the most.
Good. So we might as well assume, without loss of generality, whatever configuration we're looking at, there's no circles that could be placed anywhere. Because if there were, then we know that it would not be the most efficient. Okay. Is there, if I give you a circle configuration that's not saturated, could there be more than one way to saturate it? Absolutely. And depending on how you choose to do things, one way might allow you to put in two circles, one way might allow you to put only one. And so you could ask me maybe what is the maximal saturation possible for a given configuration. But we can just look at all configurations and just look at any one, and if it's not saturated, just make it saturated. And that will improve the density. So I was talking with Professor Stoicu before giving this lecture. I have some toys that I will be sharing if we get into random packings today. And he is allowing me to quote him. Unfortunately, I don't remember exactly what he said, but it was roughly, I hate finite boundaries. If I give you finite boundaries, the problem is very different. I can try to do this maybe with the video. Let's see if this works. It's not. Can everybody else just turn off their screens for a second? It's not letting me just do the speaker view. Excellent. I will try to hold things up. So I have brought in different containers, different bowls. So I should be doing this so the people at home can see. And some of you know I really like Rubik's Cubes, and I know there's at least 2 people here who like Rubik's Cubes. So this is a nice cylinder. I can put this in, and really, there's not that much I can do. I can't really even put in the second one. If I try, it's even worse, I can't even get one in. So the hope is that as you go off to infinity, hopefully the finite effects will not really matter. And if you think about it, maybe the area around the perimeter where I'm having issues will be small relative to the area. Which do you think will do better? Putting golf balls in here, putting marbles in here. Which do you think will be more efficient? Marbles. So this is going to be the really crude experiment. Already at 3, one of them is popping over. And again, if I had made this just a little bit larger though, I could have the third one come in. So there could be huge differences, or you might just say, I'll just cap off and just take whatever fraction, and if this goes above, I don't care about it. Marble seems to be doing significantly better. I think it's clear at this point that the marbles have destroyed the golf balls.
Marbles have like 8 times less volume. I'm not saying.
Yeah, no, and so the question is, do you think these 3 golf balls have more of an area, more of a volume than all these marbles? So, but I mean, it is a calculation that you need to do. They're made of different materials, so it's not going to be, as easy to compare. If the marbles and the golf balls were made out of the same material, how could you quickly compare the volumes? Mass, you could just weigh them. You can actually talk about how efficient is a random packing. If this was before COVID, I would have brought M&Ms in today. And we would have done, random packings of M&Ms. If people want, what I can do is, I guess the next time I go to the supermarket, I can buy the individual bags. I can give you individual bags of M&Ms. But are you allowed to eat in the classroom now? No. Oh. I can give it to you to take home and play with at home. All right, so people can share their screen again if they want to. And I will go back to, okay, so boundary issues are going to be very bad. But if we go sufficiently far out, hopefully they're not going to really have much to play with. And so they're starting off over here by saying a configuration, as I said, is saturated if you can't add anything else. All right. So given a circle configuration C, so the C is going to be the centers of our circle. Every saturated circle configuration containing C is called a saturation of C. Since the density of a circle configuration is always less than or equal to the density of any saturation, we only need to consider saturated. This is the standard without loss of generality. So we've already done one of the 4 pages. And so the last page is actually maybe a third text, but mostly it's going to just be references. Okay. So again, the reason I want to do this is I want to just talk to you about how you go through a technical paper, especially in real time. Because when you're at a conference and someone is presenting, you don't have that long of a window from when they're giving the talk to when it's time to ask questions or to chat with them afterwards. This is one of the things many of us hate about the Zoom era. It's now much harder to have conversations with people about the work they present and just bounce ideas off. Hey, that was really interesting. You've lost a lot of those interactions. And this is why a lot of us have stopped going to a lot of these Zoom conferences. For younger faculty who still haven't presented and trying to get their work out, it's still important to do that. All right. So the next thing is a Dylani triangulation in the plane with circles shown from Wikipedia. There's not that much on this page. It's basically saying that there is such a thing as a Dylani triangulation. So what is that? So a point set triangulation, so that's T of C of some discrete set of points C. All right, so we have the circle centers that we're giving you, and we're going to somehow form triangles. And we're going to form them in such a way that the plane is divided into the convex hull of the points into triangles, such that any 2 triangles intersect in a common edge or not at all, and the set of points that are vertices of the triangles coincide with C. So if we look at the example here, you can see that these 2 triangles here share this side over here. You're not having, I can't draw from, say, over here to this side, and then it would only be sharing part of the side. You either share all the side or none of the side. So the question is, if I give you a sequence of points, can you always form a triangulation line? What do you think?
No.
Okay, so why not? So let's come up with a configuration where we can't. Mm-hmm. Right. So the example that was given was if everything is on a straight line, there's no way to do the triangulation. This is a really trivial counterexample. Is there a more interesting one? What if I put 1 point off and the line goes off to infinity?
I don't think this would be possible to triangulate the plane.
Nope. We're not going to be able to get anything below this point.
And I think if one of the coordinates is bounded, you can't triangulate.
So what if all of the points live inside a giant circle? So what if there's some giant circle and all of your points live inside here? Is there any way to get the entire plane? It makes sense because if I'm going to form a triangle, I have to use 3 points. If I have n points total, there are n choose 3 ways of choosing 3 distinct points. So I only have finitely many triangles. Each triangle has only finite area. So unless we're allowing a cell going off to infinity, which we're not, this won't work. So we know immediately that there has to be infinitely many points. And they have to be going off to infinity. What if instead of a circle, what if you had some region like here where there is no points down in here? Clearly it can't be done. Do we have to worry for the problem that we're looking at that we might be in one of these situations? Why not? We're saturated. So we know there has to be a circle that we can put there. So we know we're going to have points going off to infinity. And we know we're not going to just have points on a line. So we're already seeing where the saturated assumption comes into play. Go back to paper. Okay. So does it seem reasonable that we should be able to form a triangulation like this now? Have we proven this rigorously? No. But this is probably enough detail at the level of a talk to see, yeah, I can see roughly the idea of what's going on, that I should be able to do something like this. Now, what's nice is this paper has a link that you can just click on. And so you can click on what is the Dylani Triangulation, and that picture should look very familiar. It was taken directly from Wikipedia. It just goes through and explains. And then one term that's needed is the circumcircle. The circumcircle is given a polygon, it's a circle that passes through all the vertices of the polygon. Do you always have a circumscribed circle for any finite polygon? Okay, so I see several people shaking their heads no. So we're not always going to have. And so again, I am trying to mix the different technologies. Let me know if this is working. I'm trying to balance the people here and the people at home by having things that everybody can see. And this is one impact of the zoom error in terms of how you are changing what you're doing, how much you're showing. So can somebody give me a polygon that doesn't have a circumcenter? Yes. Okay. So what is the concave kite going to look like?
Like a kite and then knock.
All the way down like this?
Yeah, and then knock the top one inside.
Ah, okay.
Actually, that original kite probably doesn't have it.
I think I was fine because I think it was far enough away that I think I would have been okay. So this is clearly going to fail. What if we had done the one I originally wanted? So how many points determine a line? So 2, unless you're in business, in which case, it's 1 point and you can just tell the boss whatever you want, whatever the boss wants to hear. But in math, 2 points determine the line. How many determine a quadratic? 3. And so once I have these 3 points, you know, if I want a circle going through them, I really don't have that much freedom. So in general, if I give you a polygon, can we expect to be able to circumscribe a circle in it? What polygons do we think we should be able to do this? Triangles. So do you think any triangle has a circle that can be circumscribed?
Yes.
All right, homework. Show can always find a circle for a triangle.
And can we assume the triangle is not degenerate?
Yes. So we will assume the triangle is not a line. And then this becomes an interesting thing as to what you consider a triangle. Is, you know, does a degenerate triangle count? We will assume the triangle has actual angle. Yes. All right. Let's say this is due Monday. So we should always be able to find something. Now, when you're trying to study something like this, it helps to explore and get a little sense of what things look like. What triangle should we start with? Equilateral. You know, if we can't understand what's going on for the equilateral, so all those sides are the same. So there's only one possibility for the circumcircle, and only one possibility for its center by complete symmetry. It has to be the middle. And so if I give you an equilateral triangle, it's got to look like that. Okay, so building on this success, let's see what else we can do. Now, again, I can at least now have my poly drawn. So I could look at now maybe a very different type of triangle. So there was the question about a degenerate triangle. That, you know, we're not allowing a degenerate triangle. But what if we had an almost degenerate triangle? With a really small angle like that. So I draw it a little bit better. So there's my triangle with a very large angle. What do you think is going to happen for the circumcircle? Okay, so in words, because we have people listening to Zoom.
It'll like balloon out.
It's going to balloon out. Going off like that. Why is this going to be bad for us? It takes up a lot of space. And what was the second thing you said?
You can't have points anywhere inside the circumcircle. So.
Right, we can't have any points inside the circumcircle. So how is this going to be bad for us? What contradiction is it going to give us? Now, I can draw, maybe my circle about this point, my circle about this point. Maybe those circles should have been a little bit larger, but whatever. It's not saturated. I can draw lots of circles in here. So I guess this is some kind of like sparkly marker. So what theorem do you think might be happening? We have two extreme cases. We have the equilateral triangle, things are as nice as possible. And we have an almost degenerate triangle, which is going to have a huge circumcircle that's not going to be saturated. Can you think of some conditions that we might want to have on our triangle?
Bound the angle.
Say that again?
Bound the angle.
Bound the angle. So maybe we have some conjecture. So do you want to make a specific conjecture? Okay, lemma 1. So lemma 1, going forward a little bit. Oops. All right, so up until lemma 1, it's just talking about how you would find the Dylani triangulation. So I'll leave that for you to look at. It seems reasonable that one should exist. And when you're giving a talk, you have to decide how much detail to go through. Has anybody here taken complex analysis? Okay, when I teach complex analysis, I usually prove the Riemann mapping theorem. And it says if you have two regions in the plane that are open sets, simply connected, and neither one is the entire complex plane, then there's a infinitely complex differentiable mapping from one to the other, which is invertible. And sometimes you can even extend it to a map of the boundary. Absolutely amazing result. To prove it fully can take between 1 and 2 weeks, depending on just how many of the lemmas, the technical lemmas from real analysis you want to do. It's sometimes not bad to see a proof that takes 1 or 2 weeks. It's a lot of stuff to remember and a lot of stuff to keep refreshing yourself about the technical ingredients you need. I need to show that this theorem can be used that all the conditions are met, that this sequence of functions has this kind of property. I can then define a new function, which is a maximization supremum of these functions, and then that will have some property. And it takes a long and long and long and long time. If you're giving a talk, you are not going to do that. You have to go in, quickly get to the key point, and get out. You have to decide which things are worth going into great detail, which things are reasonable that people can accept and move on. The existence of the triangulation, it's important, but that seems like that's something that's reasonable that we can go with. The next one, lemma 1 here, is actually the first really big part. And so what lemma 1 is saying is that the largest internal angle is at least pi over 3 and strictly less than 2 pi over 3. Is this limit trivial? Or is there some content to it? Good, which direction is trivial? At least pi over 3, because we're talking about the largest angle. Well, since the sum of the angles has to be pi, the largest has to be at least pi over 3. So that direction is trivial. The content is that it's strictly less than 2 pi over 3. It could have been as large as almost 180. And so now we have the proof over here ending with QED. We're not even looking at the proof. Does this seem reasonable? Just by looking at those few triangles in the beginning, we have a sense that something like this should be true. And again, what I'm really trying to prepare you for is when you're at conferences, either as an attendee or as a speaker. And you have to decide how much detail to give. Can you give just a quick picture to highlight what's going on and why this is true? What's the key idea? Can you summarize? When you're writing a paper, you want to put in a little bit of a summary and alert the reader. Why is this true? What's following? How is this happening? What's the key ingredient that allows us to make this advance. And the idea here is, well, if your triangle is almost degenerate, the circumcircle is going to be so huge, you're screwed. And it's not going to be saturated. And that there's going to be some critical angle where once you get to that angle, then you can no longer throw something in. But as long as the angle is sufficiently large, then the circumcircle is going to be so huge that you can put something in. Is that reasonable? What is that angle? Algebra or trigonometry. And then you do the calculation, which is in here. But that's fine. We now know at this point that something like this should be true. And as we go through the calculation, this is not unexpected. Okay, any questions on lemma 1? Okay, then it talks about the density of a triangle for a saturated circle configuration is equal to the following. What the hell does that mean? What might have been nice for it to define? Density. Right? Yes.
Wait, do we like show somewhere that like, all the triangles on theta?
No, we have not shown that yet. We've just shown that in any Dylani triangulation, you can't have a triangle whose largest angle is 2 pi over 3 or more.
Oh, but like, oh, it's talking about the density of a triangle. So for that triangle, like for they're different sizes.
Right. But when you look at it, the denominators are the same, right? So 1/2 a plus 1/2 b plus 1/2 c is pi over 2. What do you think a, b, and c are? Radians?
Yeah. Because a plus b plus c is 100.
Yep. That seems like it's the only thing that it could possibly be. It can't be side lengths.
Only depends on the area.
But I'm saying 1/2 a, 1/2 b, 1/2 c, that's always going to add to pi over 2. So are we basically just defining the density to be half the angular measurement divided by the area of the triangle? So what I would do, this is not the best way to do. I might do, no. All right, it's not letting me, oh, maybe it's, okay, I'll treat this way. Density of triangle ABC colon equals. And then it's clear that you are defining something. When I write it like this, it's not clear what's going on. This is just floating around. So this is the first part of the paper. And again, I did not read this paper before coming here. I want to do this live like you. It's unclear what it means here. I think the only possible interpretation is A, B, C have to be the angular measurements in radians. And so this is just giving you some quantity associated, and hopefully that this quantity will be useful for things. It would be interesting now what happens as I try to move this. Yes. And that's what I was afraid of. Okay. All right. So now we have lemma 2. The density of a triangle is less than or equal to pi over square root of 12. The equality holds only for a regular triangle with side length 2. If you think about a regular triangle with side length 2, well, that's going back to an equilateral triangle. So I'll go back. And so if I have an equilateral triangle with side length 2, then what we're doing is we're drawing the circles of radius 1 about each one. And that's the standard hexagonal pattern that we know and love. And so we have circles of radius 1. So if the triangles have length 2, that's exactly what we can get. Okay, so now going back to paper, they're saying that the density is less than or equal to pi over square root of 12. And so since the equality only holds for the regular triangle of side length 2, the hope is that that's going to then be our largest one. So the question is, why do you think this is the largest? So the numerator is fixed at pi halves. So really all that changes is the area of the triangle. So does this seem reasonable? Let's go through the details. So let's say B is the largest internal angle of triangle ABC. Then by the above lemma, the area is equal to square root of 3. So where was the above lemma? So I guess that was in one of the calculations of looking at the triangle with the internal angle. And so they're using the law of sines, relating opposite sides. All right, so this, that's a pretty standard result. And then noting the circumradius of the triangle by R. So if I'm let's put the lemma up over here. So the lemma should be readable. So we have our triangle A, B, C. And we're saying the area is 1/2 AB times BC times the sine of B. Okay. Does that seem reasonable?
Yeah.
So this is just, the standard results of just drawing our triangles, okay? And then they're saying it's greater than or equal to 1/2, 2 times 2 times root 3 over 2. And so where are the lengths of 2 and 2 coming for A, B, and the sine of B? Well, I know where the sine of B is coming from because it's at most 2 pi over 3.
Well, it's because the circle packing were solved so that the sides are usually too hard to fit circles.
Good. Good. So we know that these have to be at least 2. Because if not, each one of these is the center of the circle. And so we're getting a lower bound. So AB clearly has to be at least 2. BC has to clearly be at least 2. And now we know that our angle can't be more than 2 pi over 3. But it also has to be at least pi over 3. And if the angle is pi over 3, you get 1/2. So I believe let's see. So we know pi over 3 less than equal to b, strictly less than 2 pi over 3. And we want to look at the sine. So where is the sine going to be largest? For which angle?
Over 2.
Pi over 2. Right? If you think about, your trig, here's your circle. If you vary theta, the value for sine is going to be largest when theta is straight up. Right? We've seen this a couple of times that sometimes in these proofs it's really just elementary facts. What's nice about pi over 3 and 2 pi over 3, what can you tell me about their sines? It's the same. So the smallest value of sine is going to be at either extreme. So we know the sine of b is at least root 3 over 2. And that's the sine of pi over 3. And so we get that product is going to be at least square root of 3. So the density, when we calculate things, is going to be less than equal to pi over square root of 12. Okay. So now, what word scares you here? Yeah, whenever you see the word obvious, you should be very, very afraid. So it is obvious from the computation that the equality holds only when it's a regular triangle. This is a really good opportunity to talk about chasing inequalities. So when you chase inequalities, how many of you have seen a proof of the Cauchy-Schwarz inequality? All right, homework. State and prove the Cauchy-Schwarz inequality. I think it's without a t. And we'll also have this due on Monday. So it's one of the most important inequalities in mathematics. And then, when is it an equality? And so this is chasing inequalities and say, okay, I had this inequality. When am I losing anything with the approximation? And if you look at what we were doing before, we said AB has to be at least 2. Well, we were going for a lower bound. So the only way that can happen is if AB is exactly 2. Similarly, the only way it can happen is if, BC is exactly 2. And then we can look at the angle, and the only way that's going to happen is if the angle is pi over 3. Or 2 pi over 3. But it can't be 2 pi over 3 because it's strictly less than that. So it has to be pi over 3. So the only way we can have an equality is if we are in the regular equilateral triangle. Okay, so that handles this part over here. So the density of the union of any finite Dylani triangles in a saturated circle configuration is a weighted average of the densities. So here, they're at least defining something. I would put in a little symbol like this to note to the reader or the audience member that this is a definition. If you think about what's going on, when you have packings, could you have different densities depending on where you look? Yeah, I mean, if you look at a hexagonal packing, if you have a really small window, could you see a density of 0? Could you see a density of 100%? Yes. The hope is that as you expand outward, that these effects go away and that you actually get a nice true limiting value. We talked about chaos in the last lecture. We talked about changing scales. And when we change scales and zoom in, we can actually see very different answers for the density depending on where we are. And the hope is as you zoom out and out and out, and you take this giant ball or square, it doesn't really matter where the hell you center it. that the perimeter effects will be small. Professor Stoicher will not have to deal with the horrors of a finite boundary, but in the limit, it's going to be good. So now what we're looking at is the sum over all the triangles of the area of each one times the density. What's the density? Isn't that just pi halves divided by the area? And so then we're dividing by the area of the triangles. So since we have shown that the density is less than or equal to pi over 12, the density of the union is also less than or equal to pi over 12, therefore we obtain a simple proof of Thue's theorem. Is this a proof? Okay, so I will highlight obviously.
I guess the problem with any proof is like, questions how much are you assuming?
So I know what my concern is, yes.
I feel like it says finite and we want the plane.
So this is looking at the limit. So this is my question to you. Yeah. Do you buy that we have proven it? So I know we're going a little bit over, so I will end with just briefly why I have concerns. We have shown that the hexagonal lattice has the best density. Is this the density that you think of? What do we need to show about this notion of density? It corresponds to the area, to what we're thinking of, what fraction of the plane. Have they done anything to connect that? Right? At the end of the day, it looks like we have proven Thue's theorem. So my question for you is, did we actually do anything to that? Hopefully, we at least learned how to look at papers, how to read things, how to think about things. But part of this is I want to show you how easy it is to slip through things. I deliberately did.
Add a little bit.
Well, that's the question: is this salvageable? So the Ross program is prove, disprove, or salvage if possible. It's a wonderful, wonderful program for high school students. I was privileged to be involved in it when I was at Ohio State. Is there any? It all comes down to is what is your notion of density? This is not clearly stated. So think about for Friday, is there a good notion of density here? Did we actually do anything? Or did we just manipulate things and we're defining this new quantity? And we have proven with this notion of density, this is best, but this may not be the same notion of density that we think of. If there's more than one mean between numbers. There's more than one notion of density. And so the question is, if you change your notion of density, does it change? If you've done real analysis, you have different norms and metrics. You can have different open sets. The circle is coming from the standard metric of the square root of the sum of the squares. But if you do the sum of the absolute values, that gives you a different notion of what a circle would be. What would a circle be in that sense? Square. And then the packing problem is a lot easier, right? So really think about what you're choosing. If you choose the right definition, you might make the problem almost trivial. All right, so this is a good place to stop.